All right, the 1,000 sample day. Sounds pretty bold, right? Well, today we're diving into a paper that details a huge leap forward in scientific analysis. And I mean huge. We're talking about a technique that could totally change the game when it comes to the speed of discovery.
So let me just ask you this. What if you could run a whole week's worth of experiments in a single day? Just think about that for a second. That's the mind-blowing promise behind the breakthrough we're going to talk about. You know, in the race for scientific discovery, speed is everything. It's not just about getting things done faster. It can literally mean finding cures or solutions sooner rather than later. But for a long, long time, researchers in one really important field have been, well, they've been stuck in the slow lane. Until now.
Okay, so what is this slow lane I'm talking about? What's the big holdup? Why is it so hard to analyze thousands of samples at once? It really all boils down to what you could call a massive scientific traffic jam.
So the field we're talking about here is called metabolomics. And what is that? Well, think of it like taking a super detailed chemical snapshot of something biological, say your blood. It lets scientists see all the tiny little molecules, called metabolites, that are floating around in there. It's a way to get a real-time picture of what's actually happening inside an organism, chemically speaking.
And this is exactly where that traffic jam happens. See, to get that chemical snapshot, scientists have had to do it the old-fashioned way, one by one. You analyze one sample, then the next, then the next. Now imagine you have a study with thousands of samples, which is pretty normal in medicine. Yeah, that one-by-one process creates a huge bottleneck, and it just grinds research to a halt.
So let's dig into that a little bit. Let's look at why this traditional method, which is called serial injection, is just so painfully slow. The problem is literally baked into the process. Here's how it works. First, you inject a single sample. Then you gotta wait while this process called chromatography separates out all the molecules. Then you analyze the data from that one sample. And then, and this is the killer, you have to reset the whole system before you can even think about starting the next one. Now, picture doing that 1,000 times. Yeah, it takes forever.
And it's not just about being slow. This process causes real problems. The paper points out that when you're analyzing samples over days or even weeks, you start getting errors. They're called batch effects, basically tiny differences between each run that can mess up your results. It's kind of like if your coffee maker made a slightly different cup of coffee every single day. On top of that, you get these retention time shifts, which just means the data doesn't line up neatly, making it a huge pain to compare one sample to another.
So, if you're stuck in a traffic jam, what do? You don't just wait, you change the flow of traffic. And that is the beautifully simple idea behind this breakthrough approach called single-file injections, or SFI for short.
This comparison really shows you what a different way of thinking this is. Over on the left, that's the old way, right? One sample, one clean run, long wait. Then another. But look at the right. That's SFI. You're just injecting one sample after another into this continuous stream. Yeah, the data comes out all jumbled and mixed up, and it looks like chaos, but trust me, that's where the magic is.
Okay, so what is SFI, technically? Well, it's a method where you just inject samples over and over again at a fixed time interval, like, say, every 60 seconds, into a constant flow. So instead of ending up with hundreds of different data files, you get one single giant file with everything in it.
Okay, I know what you're thinking. Wait a minute. If all the data is just one big chaotic mess, how on earth do you figure out what belongs to which sample? And that is the million-dollar question. The answer? Some really, really smart software.
Here's how they pull it off. It's a two-step process. First up is the reference phase. They take a little bit from all the samples and mix them together into what's called a pooled sample. It's like a cocktail of everything. They run that first to create a master map of every single molecule they could possibly find. Then they move to the analysis phase and start injecting the real individual samples one after another into the stream.
And this quote from the paper's abstract really nails it. These researchers didn't just come up with a cool idea. They built the tool to make it a reality. They developed open source software. And that's a huge deal because it means any researcher anywhere can use it for free. And this software is what takes that giant, messy data file and just sorts it all out.
So how does this magic software actually work? Well, in a nutshell, it uses that master reference map they made at the beginning as its answer key. It then scans through that huge, continuous data stream and looks for the unique chemical fingerprints from each sample. It then matches those fingerprints back to the answer key, and voila, it can perfectly rebuild the profile for every single one. It's basically like unscrambling a really complex code.
Okay, so it sounds great in theory. It's a wild idea, but does it actually work? Well, let's take a look at the results, because honestly, they're pretty dramatic.
1,000. That's the number, the big headline. With this SFI method, they showed it's possible to analyze 1,000 samples in a single day. That's not just an improvement, that's a revolution.
But here's the really crucial part. You're probably thinking, okay, it's fast, but is it accurate? And the answer is a resounding yes. In their tests, the software got it right over 98% of the time, assigning the chemical signals back to the correct sample. So you get all this incredible speed without sacrificing accuracy. That's the holy grail.
I mean, just look at this comparison. This chart says it all, right? The old method versus the SFI method. It's not even in the same league. We are not talking about a little 10% improvement here. This is a fundamental transformation of what is even possible in a lab.
All right, so 1,000 samples a day? That's amazing. But let's zoom out for a second. Why does this really matter? What does this mean for the future of science? And, what does it mean for you and me?
Well, the benefits are just huge. First, obviously, there's the insane speed. But it also gets rid of those annoying batch effect errors we talked about, which makes the data cleaner. And maybe the best part, it's cheap and accessible. You don't need to buy some fancy new machine. And because the software is open source, any lab, anywhere in the world can download it and start using it tomorrow.
And that's the real game changer. This tech lets scientists run studies on a scale they could only dream of before. Think about it, searching for early signs of a disease across tens of thousands of patients, or of tracking pollution in the environment on a massive scale. Things that used to be logistically impossible are now on the table. It just speeds up the whole process of discovery.
So I want to leave you with this question to think about. For a long time, there have been huge scientific questions that were just too big. The sheer number of samples you'd need to analyze made them seem impossible to even try to answer. But now, when you can analyze 1,000 samples in a single day, what problems that once seemed impossible are now suddenly within reach?